Welcome to the session on Mathematica. Mathematica is a symbolic mathematical computation program, sometimes called a computer algebra program, used in many scientific, engineering, mathematical and computing fields. It was conceived by Stephen Wolfram and is developed by Wolfram Research of Champaign, Illinois. The Wolfram language is the programming language used in Mathematica. Hence, it is a system of computer programs for performing mathematical operations such as symbolic manipulation, numerical calculations, graphics and programming. Mathematica is sometimes described as a computer algebra system, probably in deference to the strong symbolic but somewhat limited numerical capabilities of its earliest versions, but it has evolved into a system that is now a very practical tool for large scale numerical calculations. Its applications can range from simple calculations to complicated programs, and Mathematica can be a powerful tool for quantitative geoscientists such as geologists, geographers, geophysicists, hydrologists and oceanographers. Because it is a general mathematics system rather than a task specific application, however, its utility may not be apparent at first glance. It does not, after all, solve specific geoscientific problems any more than do programming language such as C or Fortran or spreadsheet programs. Over the years, we have encountered many geoscientists who know that Mathematica exists but are not sure what it does with regard to the specific problems they face in their research or professional practice. The short answer is that it does nothing geoscientific in particular, but has the potential to do just about anything that a user can imagine. Computational geosciences with Mathematica is intended to help fill that gap by illustrating how Mathematica can be used to formulate, solve and visualize a variety of problems of interest to geoscientists. The functionality of Mathematica, which includes many standard packages with specialized functions in areas such as statistics and graphics, can be expanded with packages available through Wolfram Research, other commercial sources or the public domain. Packages that may be of interest to geoscientists but which are not covered here include a database access kit, digital image processing, experimental data analysis, real-time 3D graphics, fuzzy logic, neural networks, signal processing, time series analysis and wavelets. Those who are interested in those packages can contact Wolfram Research for more information about their capabilities and availability. Basic syntax. Symbols plus, minus, hyphen, exponential, star are all supported by Mathematica. Multiplication can be represented by a space between variables. A x plus b and a star x plus b are identical. On the other hand, a x plus b without a space between a and x denotes the sum of two variables, one named ax and the other b. Warning: Mathematica is case sensitive. For example, the command to exist is quit and not quit or capital quit. Square brackets are used around function arguments. Write sign of within square brackets x, not sign within simple brackets x or sign within curly braces x. Parenthesis or simple brackets group terms for math operations as in within brackets sin of x plus cos of y star tan of z plus z exponent 2. If you end an expression with a semicolon, it will be executed, but its output will not be shown. This is useful for simulations. Braces are used for list. That is, A can have the form within curly braces 81, 2, 3, which outputs within the set 81, 2, 3. Names can refer to variables, expressions, functions, matrices, graphs, etc. A name is assigned using name equal to object. An expression may contain undefined names. For example, a equal to within brackets a plus b exponent 3. The output will be a plus b whole cube. and a exponent 2 will be a plus b whole raised to 6. The percent sign or percentage symbol reproduces the value of the previous results. For example, 5 plus 3, the output will be 8, and percentage exponent 2 will give 8 to the power 2, which is 64. Basic rules of Mathematica syntax. The arguments of functions are given in brackets. Parentheses are used for grouping operations. Vectors, matrices and lists are given in braces, and double square brackets are used for indexing lists and tables. Mathematica is case sensitive, thus cos of x is not the same as capital C cos of x, and be careful. Mathematica has several built-in functions. Example, cos of x, sin of x, exponent of x, etc. The first letter of built-in functions always have the first letter capitalized, and if a name consists of two or more words, the first letter of each word is capitalized and there will be no spaces between the words. For example, Laplace transform of x. The palette basic input.nb contains symbols for common mathematical manipulations like integration, differentiation, summation, division and exponentiation. Greek symbols are also included in this notebook. The basic input.nb palette is usually open when Mathematica is started. However, it is sometimes hidden behind the open notebook. If it is open and hidden, it can be found through the window menu. The top of the window menu lists commands for organizing the window. The bottom of the window menu lists all windows that are currently active. You may see untitled 1.nb messages in addition to basic input.nb. If basic input.nb appears, select it and the palette should appear. If it is not listed, then it can be opened from the palettes command in the file menu. Note that there are other palettes available in addition to basic input.nb that you may find useful as well. The mathematical and Greek symbols in basic input.nb can be selected by clicking on the chosen symbol and then selecting each of the empty boxes and filling them in similar to the procedures used in equation editor of a word processor. Mathematica understands the Greek letter pi to be pi, that is 3.1415 etc. Mathematical manipulations can also be input through a set of standardized notation. Multiplication is represented by either a space or star. In Mathematica, A space B means A star B, but AB means you have a new variable with the name AB. Powers are denoted by A exponent or by using the symbolic representation in basic input.nb. Remember that Mathematica is case sensitive. A variable named AB is not same as variable named small letters ab. If you get no response, example Mathematica seems to be in an infinite loop or an incorrect response, you may have entered or executed the command incorrectly. You can stop execution of a command by clicking Interrupt Evaluation under the kernel menu. If you want the output from an evaluated function to be displayed as a numerical value, example in decimal format, rather than as a symbol or fraction, use the command n and the brackets. For example, n of pi will return 3.14159 and n of pi, 25 will return the number pi to 25 digits. Typing /n after the input line will achieve the same results. Example, pi /n returns 3.14159. If you wish to perform an operation on the last output that Mathematica produced, you can use the symbol percentage. For example, n of percentage will result in the decimal representation of the last output. For example, input and then evaluate pi. Mathematica will respond with p. Now type n of percentage. Mathematica will respond with 3.14159. You can also refer to specific output using output number here, or percentage output number, where output number is the number Mathematica has assigned to the cell when it was evaluated. For example, to generate the numerical value of the output designated as out of 17, the command is n of %17 or n of out of 17. Keep in mind that a specific output number will change if you re-evaluate an input line. To delete a cell, select the right bracket designated the cell and select the clear command from the edit menu. Other useful editing commands can be found in the edit menu, including cut, copy, copy as and paste. Notice that the preferences command appears in the edit menu. You can use the preferences command to set default preferences for various Mathematica operations. For example, to change the default values of fonts, you would choose formatting options /fonts after selecting preferences. Other useful editing commands are available in the input menu, copy input from above and copy output from above. The Mathematica kernel. It is helpful to understand that the Mathematica program consists of two parts, the user interface and the kernel. The user interface simplifies the process of entering mathematical equations and translates the output into easier to read symbols. The kernel is the part of Mathematica that performs computations. When you start a Mathematica session, only the user interface is running. The kernel will be launched the first time you ask Mathematica to evaluate an input cell. Consequently, it usually takes Mathematica some time to complete the first evaluation, since the kernel must be started before the evaluation can occur. After the kernel is launched, all further cell evaluations will be faster since the kernel is already started. The kernel remembers each evaluation it has performed and the order in which these were performed. This ordering is indicated by the sequential numbering that Mathematica assigns to each evaluated input and the resulting output. This ordering can be important if you have used the same variable names to designate different calculations. Occasionally, you may have performed an evaluation earlier that is interfering with a subsequent evaluation. When this happens, it is sometimes helpful to use the quit kernel command from the kernel menu and to restart the evaluation process. You can then either use the start kernel command also on the kernel menu or just select a cell to evaluate and then type shift and enter, which will launch the kernel. When you have quit kernel and then started again, you will need to evaluate cells as if they have not been previously evaluated. Plotting. The basic command to plot functions is plot of f of x, comma, within the brackets x a b, where a b is the range of values you want to display on the x-axis. Mathematica will plot symbolic functions. For this reason, Mathematica can be used to quickly provide information on the shape of a function. This is very useful for quickly viewing whether the equation you derived in your homework solution is reasonable. It is often convenient to name plots. Example P equal to plot of f of x, x a b gives this plot the name P1. Then later you can use the show command, example show P1, P2, P3 etc., where plots P2 and P3 have been defined by similar commands to show several plots on the same axis. Also, this allows the user to redefine plotting options, example the axis length, titles etc., without retyping the plot command. Several options can be used with plot or show are listed here for quick reference. Frame equal to true draws a line around a plot, default is false. Axis label with x axis label, y axis label labels the axis of a plot, the default is no axis labels. Frame labels to bottom x axis label, left y axis label, top label, right secondary y axis label labels the frame of a plot, the default is no frame labels. The last two can just be left out if they are not needed. Plot label to name places a name above the plot, the default is no plot title. Plot range to y minimum, y maximum changes the range of y axis. Plot style to curve 1 style, curve 2 style etc. changes the line styles of curves. An example is plot style to thickness of 0.02, gray level 0.05, dashing 0.05, 0.05 for a thick gray dashed line. This command needs to be used with the plot command. Equations. To define an equation, use two equal signs, that is left hand side double equal to right hand side. Equations are not functions. They are equations you must be interested in solving, that is finding the values of one or more of the variables to satisfy the equality. Analytical solutions or symbolic function generated. The command solve will find exact solutions to linear systems of equations. The command is solve equation 1 of xy double equal to equation 2 of xy comma equation 3 xy double equal to equation 4 of xy comma xy, where the equations are functions of x and y. Notice that the brackets are needed around the equations to be solved because there are more than one. Numerical solutions, number value generated. The main commands to solve equations numerically are n roots of polynomial 1 x double equal to polynomial 1 of x comma x will find the roots of a polynomial even if there are more than one root. Find root of equation x comma x initial guess will work for all equations written in the form that equation of x equals 0, not that the 0 is not included in the command, provided that the initial guess is good enough. Good enough means that find root works, not good enough means that find root does not work and you must try to make a better initial guess. In choosing an initial guess, it is often useful to examine a plot of the function. When only one initial guess is given, find root uses Newton's method. If you give a low and high range to the initial guess, that is find root of equation x comma x, low guess, high guess, find root will use the second method instead of Newton's method. Usually the second method is more stable than Newton's method, that is the second method may be less sensitive to poor initial guesses. Programming in Mathematica. A program or code is a sequence of instructions to solve some problem. In Mathematica, we input each instruction and press the return key. After all instructions are typed in, we press the enter key to execute the sequence. Individual instructions in the code can be assignment statements, iteration statements or loops, conditional like if, input or output statements, functions or other programming constructs. Looping constructs or iteration. Allow repeated evaluation of expressions. Functions do, for and while are similar to looping statements in high-level programming languages. Do function has general forms do, body within brackets k, k start, k stop, dk. Evaluates body repeatedly with k varying from k start to k stop in steps of dk. Can omit dk or both k start and dk, default values are 1. For function has the general form for, initial, test, increment, body. First the initial statements are processed, then the test condition is evaluated. If test is true, the body is processed, then increment is processed. The sequence test, body, increment is repeatedly processed until test is false. While function has the general form while, test, body, where body is a set of statements that are repeatedly processed until test is evaluated to be false. Conditionals are decision statements. High-level programming languages generally make decisions as to which processing steps should be executed next using an if structure, but some languages provide other conditionals as well. Mathematica provide the functions if, which and switch for decision making. If function, if test, true statements, false statements. If the test is true, the true statements are executed. If the test is false, the false statements are executed. Which function? Which test 1, value 1, test 2, value 2, etc. returns the first value k associated with the first true test k as tests are evaluated left to right. Switch function. Switch expression from value 1 form to value 2 etc. default. Evaluates expression and compares it to each form k in left to right order and returns the corresponding value k when a match is found. The underscore above is an optional default form, matches anything. Functional programming. Functional programming is a programming paradigm, a style of building the structure and elements of computer programs that treats computation as the evaluation of mathematical functions and avoids changing state and mutable data. It is a declarative programming paradigm, which means programming is done with expressions. In functional code, the output value of a function depends only on the arguments that are input to the function. So, calling a function f twice with the same value for an argument x will produce the same result f of x each time. Eliminating side effects, that is changes in state that do not depend on the function inputs, can make it much easier to understand and predict the behavior of a program, which is one of the key motivations for the development of functional programming. Treats computation as the evaluation of mathematical functions. Avoids changing state. Output value of a function depends only on the arguments. Eliminating side effects can make it much easier to predict the behavior of a program. In this module, Mathematica, computing system and its characteristics are discussed in detail. This module gives an account of the basic syntax of Mathematica and the basic rules for its syntax. The fundamental concepts Mathematica kernel is discussed, followed by plotting and equation techniques. We also discussed various programming constructs used in the system and briefly introduced the concept of functional programming in Mathematica. Hope you enjoy this session. See you next time. Until then, bye.